Now in the previous part, we've seen that the scatter plot gives us the overall direction, the form, and the strength of a linear relationship. Now let's look at these two graphs. The overall pattern in the first graph seems like a positive linear relationship, and in the second, again, it looks like a positive linear relationship. Now, can we compare the strengths of the relationship? Remember, we talked about how the clearer the pattern is, the stronger is the relationship. So when you compare these two graphs, the second one seems to be a clearer pattern because the points are almost forming a straight line, and they're much, much closer to the straight line that we think is the pattern of relationship between the two variables. But let me reveal to you that these are the exact same data sets, except that the only difference is that the scale on each graph is a little different. So the overall form and direction is pretty accurate when we look at the graph, but the one thing we cannot decide for sure by just looking at the graph is the strength of the linear relationship, because by changing the scale, we can make the relationship between the two variables look stronger than it really is. So if a graph will not allow us to make a final decision about the strength of the linear relationship, we need something more concrete, and that's what we have here. What we need is a number that gives the strength of a linear relationship. So the correlation or the correlation coefficient is a number that gives us the strength of the linear relationship. The relationship would have to be linear to begin with, and if it is linear, then the number which is correlation, coefficient or correlation, would give us the strength of the linear relationship. Now, the letter that is used to denote the correlation coefficient is the letter R. So R is the correlation coefficient, which gives us the strength of the linear relationship. Now, we'll never have to calculate correlation using the formula, but I just want you to look at the formula just so we know where this number is coming from, and if we had to determine whether correlation had units or not, that would be easy to see. So let's look at this. We are looking at the relationship between two variables, our explanatory variable x and the response variable y. So x has its mean x bar and y has its mean y bar. Every data set has, quantitative data set has a standard deviation. Let's say S subscript x is the standard deviation of the explanatory variable, and S subscript y is the standard deviation of the response variable. And n, of course, is the number of entries or the sample size. So using all these numbers, we can figure out the correlation. Now let's look at the parentheses xi minus x bar over S subscript x. So xi is the entries, x bar is the mean, and S subscript x is the standard deviation. If you remember, all these numbers have units. So for example, if the data is in terms of centimeters, then xi minus x bar, the answer or the difference would be in centimeters. Standard deviation also has units, and that's also in centimeters. So when we do the calculations, we have something, a certain number of centimeters over a number of centimeters. Now, using dimensional analysis, which you might have done before, you know that centimeters get cancelled, and basically this parentheses has no unit. And similarly, using the same explanation, we can say that the second parentheses which is yi minus y bar over s subscript y, has no units either. And n minus 1 is just a number. So is it clear to you that R, the correlation, has no units? So this is the first number we've come across so far that does not have units. Every other number, like the mean, the median, the quartiles, standard deviation, all have units. So R is a number that represents the strength of a linear relationship, and it does not have units. Now there are some important facts about correlation, and see if you can answer these questions without listening to my explanation by pausing the video. But the question is, will it make a difference if I switched the explanatory variable with the response variable? If the two got switched, will it make any difference in the correlation coefficient, which is R? So we look at the formula. If you look at the formula, once again, just look at the same formula. Would it make any difference if I switched the x's with the y's? Notice that the only difference is that you're going to be multiplying two numbers in a different order. Basically, instead of multiplying the data related to the x's in the first parentheses with data related to the y's in the second parentheses, you will be going y's times x's. So we know that multiplying numbers in a different order will not make any difference. So switching the response variable and the explanatory variable does not make any difference in the correlation coefficient R. Now the next question is, if I changed the units of measurement on x and y, will that change the value of the correlation? And the answer again is no. Notice that the units in the formula get cancelled anyway, and I've just explained to you that they're going to get cancelled anyway. So if I change centimeters to feet, it's going to get cancelled anyway, and it's not going to make any difference in the value of the correlation. As long as the entries, the mean, and the standard deviation are all in the same, converted to the same units of measurement, it does not make a difference in the calculation of the coefficient of correlation. Now, another thing to notice is that the correlation coefficient, R, would have the same sign as the direction of the relationship between the two variables. If the relationship between the two variables is positive, then correlation coefficient will be positive, and if the direction of the relationship between the two variables is negative, then the correlation coefficient will also be negative. Now, correlation coefficient is a number. The number lies between -1 and 1. So let's think of that on a number line. So 0 in the middle, -1 on the left of 0, and +1 on the right of 0. So the number R lies within the interval, the closed interval -1 to 1. So -1 and 1 are included. So this is how it works. For a perfectly positive linear relationship, the correlation coefficient would be 1. What do I mean by a perfect positive linear relationship? It means that the points in the scatter plot are lining up exactly, and if I join the points, I'll get a straight line. That doesn't happen in the real world, but that would be a perfect positive linear association between the variables. Now similarly, this would be perfection on the negative side. So this would be a perfectly negative linear association. So the graph would look probably something like this. All the points lining up, and when you join them, it forms a perfect straight line, and there is absolutely no variation, or the line or the points fall exactly on the straight line. So that would be a perfect negative relationship. So perfection is on the right side, denoted by r equals 1, that is, that's perfection, and r equals -1, that's perfection. Now, when do we say that the relationship between the two variables is a very strong linear relationship? If the numbers fall close to perfection, which is -1, so if the numbers fall really close to +1 and -1 or -1, then the relationship between the two variables is very strong. Now let's look at a few examples here. Notice that for 0.9, for example, +0.9, -0.89, 0.92, they all fall close to either +1 or -1. So you could say that the relationship between the two variables is very strong. Now, if the numbers are like 0.72, 0.73, 0.79, then the relationship would be can be considered to be strong. Something close to like a 0.82, you could call it a strong relationship. It's something that you have to decide and use your discretion. And maybe some numbers like 0.62 and -0.65 you would say is a moderately strong relationship. So that's just to give you an idea of looking at the correlation coefficient and then making a conclusion about the strength of the linear relationship. So let's look at this problem. It has something to do with the relationship between the price, which is in cents per pound of coffee, and how that affects deforestation. And deforestation is measured as a percent of deforestation. So that would be, so we're saying that deforestation kind of depends on the price, which means the price affects deforestation. So we take X, which is the price of coffee, to be the explanatory variable, and Y, the percentage, to be the response variable, the percent of deforestation. Now, when we look at this data, it seems like the problem suggests that when coffee prices are high, farmers often clear forests to plant more coffee trees. So it looks like it should be a positive linear relationship, because as price increases, we can assume that the deforestation percent increases based on the information that is given in the question. So in this problem, we're trying to study the relationship between coffee price and percent deforestation. So we got some data, and what we first do in order to study the relationship between any two variables is to make a scatter plot. That's the first step. So make a scatter plot. We need to know at least something about the nature of the relationship between the two variables. So the first thing we know by looking at the scatter plot is that the relationship is a straight line relationship. It's a positive linear relationship. Now, from the graph, it looks like a pretty strong linear relationship because the points seem to be close, forming a line, and the pattern seems to be quite obvious. So the more obvious it is, the stronger the relationship. However, we've discussed earlier that changing the scale can change the appearance of the strength of the relationship significantly, so we cannot depend on the graph to make a final statement about the strength of the linear relationship. But the first thing we do is to establish that at least it is a linear relationship. We also see that it is clearly positive. Now that we know that it's a linear relationship, we can go ahead and calculate the correlation coefficient, which will give us the last word on the strength of that linear relationship. So from the scatter plot, we noticed that the relationship was positive linear. We also made a conclusion, not really a conclusion, but we saw that the relationship was strong. But remember that unless we know what the correlation is, we cannot say for sure that it is a strong relationship. We need to see the number, which is more concrete than the graph, which can be manipulated by changing the scale. So we use crunch it, going to statistics and then correlation and selecting the two variables, and we hit calculate to find the correlation. Now we did say that by looking at the graph that the relationship was strong, but it seems like it is true. In fact, it is stronger than what it looks like in the graph. Remember what we talked about? Correlation is a number that goes from -1 to +1. The closer it is to -1 or the closer it is to +1, the stronger is the relationship. Now 0.9556 is very close to +1, so we could say that the relationship is very strong. So correlation is a numerical summary that tells us something about the strength of a linear relationship. So that's the reason why we first established that it's a linear relationship before we calculated R. Because if the relationship is not linear, then basically the number R doesn't make any sense. It doesn't really say anything. So we need to first establish that it is linear before we calculate the correlation coefficient R, which tells us exactly what the strength of the relationship between the two variables is.